One nice aspect of laziness is that it makes it easy to deal with infinite amount of works. Just do everything only when it is demanded. Following this principle, we look at ways to define and manipulate infinite streams. You saw that all elements of a stream except the first one are computed only when they are needed to produce a result. One maybe surprising possibility this opens is to define infinite streams. So for instance, the stream of all integers starting from a given number could be defined like this. You would say def from of an int equals the stream consisting of n followed by from n plus 1. Now normally, of course, this would be a non-terminating recursive computation, but because the stream cons operator is lazy in its right operands, the from n plus 1 here would be actually calculated only if somebody is interested in the second element of the stream that's defined here. So using from, we can now write infinite streams. For instance, the streams of all natural number would be from 0. Or the stream of all multiples of 4 could be the stream of all natural numbers mapped by times 4. So take each natural number, multiply it by 4. That gives a stream that returns all multiples of 4. So let's see this in the worksheet. I've already defined from. So a stream of natural numbers would be from 0. The stream of multiples by 4 would be the natural numbers mapped by times 4. To see it in action, I could then take M4S and take, let's say, first 100 elements and convert the whole thing to a list, which would force it. So there I would indeed see the list that contains the first 100 multiples of 4s. But of course I could go higher. I could take the first 1000 and I would get the first 1000 elements and so on. Now one problem where we can put these techniques to good use is in the calculation of prime numbers. There's actually a very ancient algorithm called the sieve of Eratosthenes to calculate these numbers. The idea is as follows. We start with all integers starting from 2. So 3, 4, 5, 6, 7. And so on. We take the first number, that's a 2, and that's a prime number. We then eliminate all multiples of 2, so that would be the 6, the 8, the 10. The first number left in the resulting output stream is 3, and that's a prime number. We then eliminate all multiples of 3, so the 6 is already eliminated, 12 is already eliminated, 15. The first number that's left in the stream is 5, and that's a prime number. We eliminate all multiples of 5, and so on. So in each step, we take the first element of the remaining stream of numbers. That one is a prime number. We eliminate all its multiples, and we repeat. So here's a function that implements this principle to the letter. To sieve a given stream of numbers S, what we do is we take the first number in the stream, so that would be our presumed prime number, and we follow it with all numbers that are not multiples of the first number. So we take the rest of the stream and we filter it with the predicate that we say, well, the number modulo the first number, the s dot head, must be different from 0. So once we have the sieving method, obtaining all prime numbers is really easy. We simply say the prime numbers is sieve of all the integers from 2. Let's try it out. Primes let's take the first prime numbers and convert it to a list. And there you go, the first prime numbers here on the right. So let's get back to square roots one more time. The previous algorithms we've seen for the square root algorithm always mix the termination criterion is good enough with the method to calculate new approximations. With streams at our disposal, we can now express the concept of a converging sequence without having to worry about the termination criterion. So we could write a stream that represents all the successive approximations of a square root of a given number. The thing we would do is we would have the usual improve method, and then we would say, well, we have a lazy val guesses, which is a stream of double, and the guesses start with 1, and each successive value is obtained by mapping the improve function over guesses. So this might look highly alarming to you, a little bit like a snake eating its tail, because what happens here is that you apply a map operation on the value that you're about to define. So won't this blow up in an infinite recursion? Well, again, no, because we have the operation stream cons here, which is lazy in its right operand. So everything actually works out as it should. You can convince yourself by going to the worksheet. I've given you precisely the same stream method. So let's try to apply this to a number, let's say 4. Take the first 10 elements and print it out. So what we would get is a perfectly good stream of approximations to the number 4, which after a couple of iterations converges to 2.0. So now we have decoupled the idea of a converging sequence from the termination criterion. Of course, we can add the termination criterion later. You see that here. So we have defined the isGoodEnough function as before, and we can then subject our square root stream to a filter method of all the elements that are good enough approximations. So let's do that in the worksheet. I've added the isGoodEnough method, and then let me just filter that. Filter is good enough with respect to my number 4, and I want to show the first 10 elements. So what you see now is you get a stream of solutions that are all already good enough approximations to the actual square root value. So you could just take the first one of that stream and return that as the result of your computation. So here's a quiz for you. Consider the following two equivalent ways to define an infinite stream of multiples of a given number n. You could write from 1 map times n, as we've seen, but you could also write from 1 filter modulo n equals 0. Both expressions would give you the stream of multiples of n. But which of the two expressions generates its result faster? Would it be that expression here or the filter down there? So let's see how these two expressions would behave. Let's take, for the sake of the example, n equals 3. So the first expression would produce first all the elements of the natural number starting from 1 and immediately multiply each of these by 3. So it would yield in that order 3, 6, 9, 12, and so on. The second expression would produce all natural numbers as before, and then it would filter these numbers to keep only those that are divisible by 3. So it would keep, the filter operations would now keep every third number in the stream. So by that argument, the map operation is more efficient because it doesn't generate unnecessary stream elements that are filtered out afterwards. So my vote goes to answer 1.